Lecture 12.02, Series. This slide shows the Columbia River Gorge and Mount Adams, the second highest mountain in the state of Washington. The previous photo was taken from just behind this monument. This Stonehenge replica is a Klickitat County World War I memorial located near Mary Hill, Washington. Start with a square 1 unit by 1 unit. We section off half the square, so we have an area of 1/2. We take half the remaining area, which has an area of 1/4. And we keep adding. The next section has an area of 1/8, then 1/16, 1/32, 1/64. And if we keep going like this forever, we will have filled in the entire square, and we will have an area of 1. This is an example of an infinite series. This series converges, that is, it approaches a limiting value. In an infinite series such as this, a1 plus a2 plus a3 and so forth equals the summation from k equals 1 to infinity of a sub k. a1, a2, etc. are terms of the series. A sub n is the nth term. We can find partial sums. S sub 1 is just the first term, a sub 1. S sub 2, or the second partial sum, is a sub 1 plus a sub 2. S sub 3 is a sub 1 plus a sub 2 plus a sub 3, or the sum of the first 3 terms. So S sub n is the sum of the first n terms. We write the summation from k equals 1 to n of a sub k. So this is the nth partial sum. If S sub n has a limit as n approaches infinity, then the series converges. Otherwise, it diverges. Geometric series. In a geometric series, each term is found by multiplying the preceding term by the same number r. We'd have a plus a times r plus a times r squared plus a times r cubed plus, and we keep going, the general term is a times r to the n minus 1. So the sum is the summation from n equals 1 to infinity of a times r to the n minus 1. This converges to a over 1 minus r if the absolute value of r is less than 1, and diverges if the absolute value of r is greater than or equal to 1. We say -1 is less than r, which is less than 1. So the interval from -1 to 1 is the interval of convergence. Example, 3 over 10 plus 3 over 100 plus 3 over 1,000 plus 3 over 10,000, etc. Could also be written as 0.3 plus 0.03 plus 0.003 plus 0.0003, and so forth, which is equal to 0.333 repeating, which we recognize as 1/3. We can confirm this by taking the first term, 3/10, over 1 minus r, and r is 1/10. So 3/10 is a, the first term, 1/10 is r, the ratio. So we get 3/10 over 9/10, or 3/9, which is 1/3. Example 2, 1 minus 1/2 plus 1/4 minus 1/8. The first term is 1. The common ratio is negative 1/2. So the infinite sum is 1 over 1 minus negative 1/2, where 1 is a, the first term, negative 1/2 is r, the common ratio. So we get 1 over 1 plus 1/2, 1 over 3/2, which is 2/3. The partial sum of a geometric series is S sub n equals a times 1 minus r to the n over 1 minus r. If the absolute value of r is less than 1, then when we take the limit as n goes to infinity of a times 1 minus r to the n over 1 minus r, r to the n approaches 0. And we get a over 1 minus r. If the absolute value of x is less than 1 and we let r equal x, then we'd have this series, 1 plus x squared plus x cubed plus dot dot dot, which sums to 1 over 1 minus x. The more terms we use, the better our approximation over the interval of convergence. The first requirement of convergence is that the terms must approach 0. The nth term test for divergence says the summation from n equals 1 to infinity of a sub n diverges if the limit as n approaches infinity of a sub n fails to exist or is not 0. Note that this can prove that a series diverges, but cannot prove that a series converges. Example, the summation from n equals 0 to infinity of n factorial times x to the n. If the absolute value of x is greater than or equal to 1, then n factorial x to the n grows without bound. But if the absolute value of x is between 0 and 1, then the limit as n approaches infinity of n factorial x to the n equals the limit as n approaches infinity of n factorial over 1 over x to the n equals infinity. Note that as n approaches infinity, eventually n is larger than 1 over x, therefore the numerator grows faster than the denominator. Therefore, the series diverges, except when x equals 0. Another series for which it is easy to find the sum is the telescoping series. For example, the summation as n goes from 1 to infinity of 1 over n times n plus 1. Using partial fractions, we have 1 over n times n plus 1 equals a over n plus b over n plus 1, Multiplying through by the common denominator, we get 1 equals a times n plus 1 plus b times n. Clearing the parentheses, we have 1 equals an plus a plus bn. So 1 must equal a, and 0 must equal a plus b. Therefore, 0 equals 1 plus b, or negative 1 equals b. Now we can rewrite our series as a summation from n equals 1 to infinity of 1 over n minus 1 over n plus 1. Generating the first few terms, we get 1 minus 1/2 plus 1/2 minus 1/3 plus 1/3 minus 1/4, and so forth. But we notice that parts of the terms cancel. We can cancel a negative 1/2 and a positive 1/2, and a negative 1/3 and a positive 1/3. And so the third partial sum is 1 minus 1/4. The nth partial sum would be 1 minus 1 over n plus 1, because we could just keep canceling. If we take the limit as n goes to infinity, we see that the sum of the infinite series in this case is just 1. For a telescoping series, the summation from n equals 1 to infinity of b sub n minus b sub n plus 1 converges to b sub 1 minus the limit as n goes to infinity of b sub n plus 1. One important series that comes up frequently in calculus is the harmonic series. A harmonic series has the form summation from n equals 1 to infinity of 1 over n, which equals 1 plus 1/2 plus 1/3 plus 1/4, and so on. Those of you who were in BC calculus know that the harmonic series is divergent, but we did not learn why. In this case, it is helpful to look at some partial sums. S1 is 1. S2 is 1 plus 1/2. S4 is 1 plus 1/2 plus 1/3 plus 1/4. And notice we've grouped the last two terms together. And 1/3 plus 1/4 is greater than 1/4 plus 1/4, or 1/2. So S4 must be greater than 1 plus 2/2. S8 is equal to 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8. And we've grouped the last four terms together. S8 then is greater than 1 plus 1/2 plus 1/4 plus 1/4 plus 1/8 plus 1/8 plus 1/8 plus 1/8. Or S8 is greater than 1 plus 1/2 plus 1/2. So S8 is greater than 1 plus 3/2. We follow a similar pattern for S16. So S16 is greater than 1 plus 1/2 plus 1/4 plus 1/4 plus a series of 1/8 plus a group of 1/16. Simplifying, we get S16 is greater than 1 plus 1/2 plus 1/2 plus 1/2 plus 1/2, or S16 is greater than 1 plus 4/2. The pattern that emerges here is S sub 2 to the n is greater than 1 plus n over 2. Since the limit as n goes to infinity of S sub 2 to the n equals the limit as n goes to infinity of 1 plus n over 2 equals infinity, the harmonic series diverges.